Okay, so the natural logarithm has this definition using an integral. So we're integrating from 1 to x in this function 1 over t. And we did a few things last time. We started by looking at the graph of 1 over x and then working through a few properties of the natural logarithm, like when you plug in 1 in your integral, you're integrating from 1 to 1, so you get 0. And on the graph, this corresponds to the area of this vertical line. And lines don't have any area because they're not really two-dimensional, they're kind of one-dimensional. Okay, and then we also talked about the natural number e, or the Euler number, and it's the number where that when you plug it into the natural logarithm, you get 1 out of it. And it's about 2.7. You've probably seen e before. And then we have the derivative of the natural log is 1 over x. So something from calculus 1 that you might remember is that, well, in calculus 1, you didn't have a function whose derivative was x to the minus 1, right? Because the power rule works like this. And the only way to get a minus 1 out of the power rule would be if you had a 0 in the exponent, but that would be the constant function, and you'd actually be multiplying by 0. So there's no way to use this to get a minus 1. So the natural log fills in that gap. And if you're hearing background noise, that's rain. Hopefully it's not too loud. Okay. And this is where we finished up last time. We looked at lots of examples, or at least 3 of them. And the last example was this one. The derivative of the natural logarithm of an absolute value is 1 over x. So adding this absolute value in here, even though it is this more complicated function than just 1 over x, or sorry, than just y equals x, which is a single line, adding the absolute value function doesn't change the derivative, and also has the benefit that we can plug in x values that are negative, because when you put in a negative number in an absolute value, you get something positive, which means you can plug it into the natural logarithm. And before we move on, this also has another consequence, because we know an integral undoes a derivative, essentially. So if we know the derivative of the natural log of the absolute value of x is 1 over x, then that means we also know the integral of this function. So that's going to be the first property that I put down here on my list. And last time we got up to property number 3. So this is number 4. So the integral of 1 over x dx is equal to the natural log, and then we need to put, okay, I got a warning that my connection was unstable. Hopefully it's fine now. Okay, so when we integrate 1 over x dx, we need to be sure to put in an absolute value here in our natural logarithm. And the reason for this is that we want to allow there to be negative values of x. Okay? And if we don't have this absolute value here, then we can't have negative values. And I should mention here that even though we can allow negative values, we still can't allow x equals 0. because there we would get a division by 0. Don't try to divide by 0. Moral of the story. Okay, and since we're talking about natural logarithms, well, you probably know lots of properties of logarithms, and well, they still are true, even if we think of the natural logarithm in this more complicated kind of way, using integrals. Like if we take the natural log of b times x, so I'm multiplying my x by a constant, we know that this splits up into addition. So this is the natural log of b plus the natural log of x. So this is just the usual multiplicative property. And there's another corresponding property for division that you probably know. So if I have the natural log of b divided by x, then instead of adding, we multiply. So this would be the natural log of b minus the natural log of x. Okay, and then I'm going to write a couple more properties, and then before we move on to anything else, I want to make sure we go back to the definition, so that complicated integral definition, and make sure that this actually works. So what we know to be true from, say, our algebra class, does it actually work if we use this calculus kind of definition? And then a couple more things. So if I take the natural log of 1 over x, then what I get is actually negative log x. So we can flip the fraction, but we pay for it with a minus sign. And then one more property. If I have x to an exponent, then I can move that exponent to the front. And over here on the side, I'm going to say that r needs to be a rational number. So there's a reason for this that I don't want to get into. Having to do with proofs and that kind of thing. So it's a bit technical. But so we can have fractions up here for now, but maybe not more complicated numbers like pi. And like I said, the reason is proof based, so not something that we're going to worry about too much in a calculus class. Okay, any questions about these properties before I flip the page and we talk about this one in more detail? Okay, so I said we're not going to worry too much about proofs, but I do want to at least look at one of these things. So this is the multiplicative property for the natural logarithm. So how do we know this is true? That's the question. Well, it turns out that it has to do with derivatives. What I mean is this. So consider if we take the derivative of this function, the natural log of bx. This is the sort of thing that we did on Friday. We would have to use the chain rule, so we get 1 over the inside of the logarithm, so 1 over bx. And then we would have an inner derivative, so we have to take the derivative of bx. And b is a constant. That means we're just left with b. And the b's cancel, so we get 1 over x. Okay, so we've already seen this, like I said last time. And another thing I want to point out, just so that we remember, the derivative of just the natural logarithm of x, you should remember, is also 1 over x. So what we have are two different functions, the natural log of bx and the natural log of x by itself, but their derivatives are the same. So does anyone remember something maybe from Calculus 1 about what happens when two functions have the same derivatives? So let me start writing a sentence. So since these two functions, the natural log of bx and the natural log of x, have the same derivative, how would we fill that in? Anyone remember?
Oh, it means they intersect, right?
Intersect. Um, how would we tell that? I guess what I should remind you, derivatives tell you the slope of functions. So what these two derivatives being equal to each other means is that the two functions have the same slope. And if two functions have the same slope, what does that mean? And I'm asking you to think way back to Calculus 1, so it's fine if you're not completely sure. Since they have the same slope, no matter what value of x we plug in, we know that they differ by a constant. So we know that the first function, let's say, the natural log of bx, is equal to the second one plus some constant. Maybe I can do a quick little sketch up here just to explain. So if you have two functions with the same slope, that means they have to look the same. So I can start drawing one function maybe like this. Maybe this is f of x. If I know another function has the same slope, I know that it has to match the shape of this function, but maybe it could be shifted up and down. So maybe it's up here. So this would be something like f of x plus a constant. And that's what I'm getting at here. They have the same slope. That means they differ by a constant. They're just shifted up and down. So at this point, we're actually pretty close to what we want to conclude. So we have the natural log of bx on the left side of an equation, and then we have the natural log of x plus a constant. So the only thing that's left to do is to figure out what this c, the constant number, should be. And we already know the answer, what it should be. We just have to determine it for sure. And the way to do that is to plug in a value for x. So to find c, plug in x equals 1. So this is the easiest number to plug in because if we plug a 1 into the natural logarithm, we get 0. So this will go away. Okay. So let me write it out. So we're plugging in a 1 there, so we get a b times 1 on the left side. On the right, we have a natural log of 1 plus c. B times 1, that's just b. So we have a natural log of b. Natural log of 0, sorry, the natural log of 1 is 0. So we're left with c on the right side. And there we go. This constant is actually the natural log of b. So if you wanted to write a concluding sentence, you could say your conclusion over here, since c is equal to the natural log of b, we can plug it in here to conclude that the natural log of bx is equal to the natural log of x plus the natural log of b. Okay. And since we're writing a proof, we'll put a little end of proof symbol, a little square. Any questions over that little explanation? Okay, so no one's saying anything. I guess that means everyone's happy. But if any of you are curious about how the other properties work, so maybe you want to work through the details, you would want to do something exactly like what I did. Like if you wanted to prove property 6, you would take the derivative of this and compare it to the derivative of the natural log of x, and then try to fill in the rest of the details. And if you like that sort of thing, this is a fun little problem. Okay, so let's move back to calculus. And do this example here. So I want to integrate this rational function. So this is a bit more complicated, or at least more complicated looking than the kinds of functions that you can integrate in calculus 1. But we're going to be able to do it using the idea of the natural logarithm. So our rule here that we're going to use is this one, and maybe I can put a y in. Well, let's just leave it at x. Okay, so excuse me. I should state it like a u substitution. Back on our properties page. So for those of you following in the notes, I'm going to skip back to our list of properties. I should actually write this one out for you. So we're on number 8 there. The next one will be 9. And this one has to do with u substitutions, like I said. So the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. So far, this looks exactly like this simple basic rule. But here, I want to think of u as another function. So u needs to be differentiable, meaning we can find its derivative. And we also need to make sure we're not trying to divide by 0, so u can never be 0. Okay, so add that property to your list because we're going to need it on this next integral. Because now in the denominator, we can see that we have not just x by itself, we have a function. And I want to do a u substitution. And on this first one, I'll just tell you that the u substitution should be the denominator. And this is something that you'll have to do on your homework as well. So we're going to say u is equal to y squared plus 25. And we know that we also need to find du. So just like in the formula here, we have 1 over u times du. We'll need to find that here as well. What is du, anyone?
2y dy?
2y dy. Perfect. So in the denominator, we have u. Where is du? Where do we find it? I guess what I'm asking is there anything left over? Do we need to multiply by some number?
Shouldn't it be 1/2 du?
1/2 du equals y dy. Yeah, that's one way to think about it. I think there's several ways that would work. Yeah, and then this way we can collect the y and the dy and plug in 1/2 du. The other way that I would think about it is to think of 4 as 2 times 2. So 2 times 2y. And then you can just collect the 2y with the dy, and that'll become your du. Okay, so either way you think about it, you're either dividing 4 by 2 or you're factoring a 2 out. Either way, you'll get a 2 left over. And then your du, that's the 2y dy. And then the denominator is u. So what's my integral? And we can make this look a little bit more like the rule. If we pull the 2 to the front, and we can even write it this way. Instead of du over u, I can write 1 over u times du. But what is my integral? According to the...
Is the natural log absolute value of u plus c?
Yeah. Right, and don't forget about the 2 in the front. Okay, so we're almost done. The only thing left to do is to plug this back in. So as our last step, we would say, hopefully I don't run out of room here, the natural log of y squared plus 25 plus c. Good. Any questions over that u substitution example? No. Okay. So one thing I want to make sure we think about before we move on, why absolute value? It's because in the natural logarithm function, going way back to the definition, this definition using an integral only makes sense if we plug in positive numbers. The reason would be to this graph of 1 over x. So you remember 1 over x has this vertical asymptote at x equals 0, which corresponds to where you divide by 0. If we try to plug in a negative number, we would be starting here at x equals 1 and then integrating to the left this way. So in order to integrate that way, we would have to somehow cross this vertical asymptote, which isn't possible. Okay, because it blows up to infinity that way, and it also blows up to negative infinity down here. So we can't hop across it. It's a good question, though. And yeah, no problem. And something to think about on this particular question, back in the rule, I said that our function, our u, has to be differentiable and never 0. So let's just think about that for a second for this particular one, the y squared plus 25. So first of all, is it differentiable? Well, yes, we already took its derivative when we were doing this. But the one that I want to think about is this one. Is y squared plus 25 ever 0? What do you think?
No,
No, it's not. And why not?
because even if you use the negative number, the square would make it positive.
Right. So when you plug in anything here into y squared, you're always going to get a positive number. Perfect. Yeah, that's exactly right. And if you graphed this function, you would see that it never crosses the x-axis if you just graphed it quickly. Okay, so let's leave that problem there and move on to this one. We're going to try to integrate tangent. So if you think back to calculus 1, you probably remember all of the derivative rules. So maybe you know how to find the derivative of tangent. And you also know how to integrate functions like sine and cosine, and maybe a few others, secant squared, cosine squared, that kind of thing. But you probably don't know what the integral of tangent x should be. And that's because in order to find its antiderivative, we actually have to use this natural logarithm function. And the way to think about it is by breaking the tangent into its two pieces. So what I mean is tangent is really sine over cosine. Like this. And in order to integrate this function, we're going to have to do a u substitution for the denominator. Just like the example above. So u is going to be cosine x. What is du? What's the derivative of cosine?
Is it negative sine?
Right. Minus sine x. And tag on a dx. Okay, and let's think back here. So in this example, the first example, our u was never 0. Is cosine ever 0? What do you think?
Yes.
Right, it is definitely 0. And I should have enough room here to do a little sketch. Just sketch a little segment of it. Let's put in a few marks. So maybe here's pi over 2, here's pi, and then minus pi over 2, minus pi. So we know cosine of 0 is 1 up here. And then when we go to pi over 2, maybe think to the unit circle. So we start here, the x-coordinate. The x-coordinate up here is 0, so it goes to 0. And then as you go around the circle, it goes to -1 on the x-coordinate. Something like that. And this is symmetrical. So if you go around the circle the other way, you get to 0. And then -1. So it definitely does have zeros. So in order to do this u substitution, we have to be careful. We have to make sure we don't include those in our domain. So I'm going to have to say over here that x needs to stay between these two numbers. So it needs to stay between minus pi over 2 and positive pi over 2. Okay, so this is a technical detail, and there's a really good reason for it. If you think to the graph of tangent, so here's cosine x. Let's do tangent x over here. If you've ever taken a look at the graph of tangent, you'll know that it has these vertical asymptotes at minus pi over 2 and positive pi over 2. It looks something like this. So it blows up to infinity there. And that's why we can't include these values here, because of this blow up asymptote. Okay, so that was kind of an aside. Let's think back over here to our integral and plug in our u and du. In order to use this du, we'll have to somehow get rid of the minus sign or incorporate it. The way that I would like to think about it is to put a minus sign on both sides, just an extra minus sign. So positive sine x is negative du. So when we do our u substitution, we're going to pick up a minus sign. Like that. Okay, and then you can write this minus sign here like I have, or you can put it in the front. It doesn't really matter because it's just multiplying by -1, a constant. So you end up with an antiderivative of this with a minus sign, so minus the natural log of u, or the absolute value of u, plus a constant. And then working back, plug in your u, so minus the natural log of cosine x inside an absolute value, plus c. Okay, so if I stopped here and you went and looked at your textbook, maybe you wanted to see what in the back there's a list of rules for integrals. Maybe you went back there to check to see if this was right. And you would actually see something different. Here is what you would see in your textbook. Instead of minus the natural logarithm with a cosine inside, you would actually see a secant. Like this. So can someone tell me the relationship between this negative natural log of cosine and the natural log of secant? Why are these actually the same? Or asking it another way, what's the relationship between secant and cosine? Right, Matthew in the text said they have an inverse relationship. So secant is actually equal to 1 over cosine. So if I take the natural log of secant, I'm really taking the natural log of 1 over cosine, like this. And if we think back to the properties of the logarithm, number 7 in this case, when we have 1 over something in our natural logarithm, we can flip our fraction and pick up a minus sign. So we can do that here with cosine. We pick up a minus sign and flip the fraction like so. So these two really are the same, but this is the way that you'll usually see it written. Any questions? Okay, and now I want to wrap up class a little bit early today with a list of integral formulas similar to this one. And that's going to be the first formula, number 1. The integral of tangent is the natural log of the absolute value of secant. And there's a few details that I'm going to leave off of these integral formulas. So like in this example, we saw that x had to be between these two values, between minus pi over 2 and pi over 2. And there's going to be similar properties for each of these formulas. The idea is that we have to make sure the denominator and the integral isn't ever going to cross 0. So my next one is for cotangent. And its integral is the natural log of sine. And remember, cotangent is instead of sine over cosine, cotangent is cosine over sine. So you would have to make sure your sine in the denominator is never 0 for that one. And you can find those details in your textbook, or you can think through, what the graph of sine looks like and come up with it on your own. Do a tiny little graph for sine. Looks something like this. So for sine, you would want to stay between these 2 points. Maybe you remember what those are. 0 and pi. Oops, that's not number 2. Third one. This one is for secant. So you already know that the integral of secant squared is just a tangent, but if you have a single secant, it's more complicated. It's the natural log of secant x plus tangent x, both inside of absolute values. And then our last property is for cosecant. And you should know that the integral of cosecant squared is negative cotangent. But when you only have the single cosecant, it's more like this one. You'll get a natural logarithm with a minus sign on it. And then cosecant plus cotangent inside your absolute values plus a constant. Okay, so these are 4 new integral rules that you should add to your memory bank, along with the ones that you learned in Calculus 1. And that's our stopping point for today. Are there any questions?